And the next talk will be Advanced Data Transformation Pipeline for AI Portfolio Management by Michael Noureddine and Philippe at Advestis. Please go ahead.
Thank you very much. Hello, everyone. We are glad to be here with you in Dask Summit 2021. I'm looking forward to talk about advanced data transformation pipeline for artificial intelligence portfolio management. So the agenda of this presentation is like the following one. The first, we will talk about shortly about attendees. Next, it's about implementation of Dask and the context. And finally, the conclusion. So who we are. Advestis, it's a contract research organization, a CRO, with a deep understanding and practice of interpretable artificial intelligence and machine learning techniques. As research partners, Advestis leverage their specialized R&D and innovation resources of its clients. Sponsors and clients increasingly rely on contract research organization for cost-effective co-development. Our experience and focus are concentrated in two key sectors, which are financial sciences and hydrogen sciences, where we provide a contract research services to financial institutions and hydrogen value chain operators. And this presentation will be given by my colleagues, Mike, Philippe, and myself. Mike is a senior DevOps engineering and a lecturer at Dauphine University. And Philippe is a lead Python engineer and data scientist. For myself, my name is Noureddine. I am lead data analyst. And we will talk about a project that we have been working on. And in general, we know a data science project goes through 4 or 5 steps. The first one, it's the raw data selection. The second, it's cleaning and doing the feature engineering on the primary data or the raw data. Third, it's running training models. Fourth, it's making prediction, or in our case, making sales or buy recommendations. And finally, it's exploiting and visualize the results. In our application, we'll focus on study the second part, which is the feature engineering. And the context and the data we'll use, it's about the shares or stocks that make up the stock 600 shares index. And every stocks has attributes such as price, AG scores, market capitalization, dividends, etc. And the total of attributes that we have, it's 276. And every attribute has 10 years history in business days. And with 100 columns for every stocks and 1,000 columns for every stocks and 2,600 for rows, which is dates. And if we multiply the number of tables times the number of columns times the number of dates, we have about 700 million cells. It's a lot of cells. Then the challenge here is to run 100 of operations, which are complex or simple, without blowing up the RAM and in a reasonable time. And it's a sample example of operation that we do in the feature engineering that we call also derivations. We have, for example, temporal z-score, which allow to make a variable stationary, or we have correlation operations, standard deviations, temporal shift, etc., etc. So we can imagine our process here like a graph of calculation, like the following one. And you have in the left the input data, the raw data, which is prices, AG scores, etc. And the start line, it's our operations. And the middle, we have the intermediate data, which generated by the derivations. That it's additional data from the primary data. And the left, we have the results and the output of our operations. So what would we like to do here is to do the parallelism computation, and for example to run a subgroup of group in order to save time, for example. So if we have the possibility to run a subgroup here, the graph it will be like this one. If we want just to run returns per sector, that we like the process will skip the volatility and the volatility per sector. So here this is why we choose Dask, because it answers perfectly to the problem mentioned before, and this for the next I let you with my colleague Mike. Thank you.
Thank you, Noureddine. So let me share my screen now. Okay, so regarding our requirements, we needed distributed computing. We code in Python, so Dask was a good candidate for that. Let me sum up our constraint. So we have a graph for more than 1,000 nodes, and to optimize its execution, we need to cache intermediate results to avoid running the same nodes multiple times. Okay. And the second constraint, as Noureddine explained, we have to be able to run a subset of our graph just by selecting a few final nodes. So considering Dask, we have two options on the table. First option is Dask Future. Second option is Dask Delayed. So let me refresh these two options, these two primitive, Dask primitive, and do a short comparison and check which option is best candidate for us. Okay. Okay, so a bit of Jupyter Lab. First step, let me start a Dask cluster. So for those who don't know how to run a Dask cluster, it's quite simple. It's straightforward from this Dask extension. So my cluster is now running. I can inject this code to get a client object pointing to our Dask cluster. I've got access to the Dask console. So with progress and stream, this guy, yeah. Okay, so let me run some code. So client object is in memory now. I import Dask. Let's start with Dask Delayed. So it's a part from the Dask tutorial. So for those who know this Dask tutorial, it's quite simple. We have here two functions. The first function is an increment. Second function is an add function. We have a decorator Dask Delayed. So we have here we are able to build some delayed object. Okay, and now I'm building this object. So three objects, X, Y, Z. And X and Y are incremental values, and Z is the sum of X and Y. With delayed, I can visualize the graph. It's pretty cool, and I can compute this graph. On your right, you can see that we have three tasks. The first two tasks are green for the increment. Then we have the add function. Okay. So if if I compute a Z2 now with another Y object, Y2, again, so here we compute again the X object, and we obtain the Z2 value. So it means at the moment we don't have any cache. The X object is not cache. So solution to cache this information in memory. The information is stored, the memory is distributed in the Dask cluster. I can use the persist, I can call the persist method. If I run persist method, my X object is run again. Then if I play with the Z object, I compute Z. The only execution now is the add function. So it means it confirms that the X object is stored in memory. So conclusion for the Dask delayed. So advantages for Dask delayed. We have the visualize method, and also delayed are lazy object. It means we can set up many delayed objects and run only and call only a subset of these objects. But disadvantage, the persist method has to be implemented explicitly. So regarding our use case, that's not enough. Okay, so let's continue with the future. Okay, so again, I'm cleaning up the memory. So with future, we have the same function in can add, but without any decorator. Okay, now to build a future, I call this method client submit. My future starts with a pending status, then is executed immediately. We can see that on the right. And I can call the result for X. Again for Y. Here, Y a bit different. So Y corresponds to the add function, add of X and 2. We can see that the add function has been, only the add function has been called. So for futures, the results are stored in memory. Okay, so conclusion for Dask futures now. So for Dask futures, advantage, persistence is automatic, and the other advantage is that the persistence lasts as long as we have object pointing to the futures. So we can finally handle the life of this persistence. Disadvantage, future is triggered without delay, and there is no visualize method. That's fine, or at least I don't know if there is any visualize method. So it doesn't solve our constraints out of the box. It means, so first conclusion, we need something more. So we have developed a thin wrapper on top of actually futures. Why? Because future persists automatically, and its persistence is finely tuned. Okay, and now Philippe will deep dive into this thin wrapper. Thank you.
Thank you, Mike. Can you just stop sharing your screen, please? Thank you. So here we are. So, okay, so as Mike said, we need an additional layer of code on Dask to do what we want to do. Before deep diving into it, I will show you a bit about the operators we use in our derivations. Quickly, we have mainly three kinds of operators. Unary operators, taking one input and giving one output. more generic or n input operators, being able to take many inputs and giving only one output. This would be, for example, storing z-scores into sectors. You could take z-score and sectors into input and give one data frame as output. Finally, we also have map. Like, map will use one unary operator, but use it on many inputs at once and give one output per input. Now, about the code itself, if we want, for example, to have a derivation, we could have this derivation toy model. Here we would take prices in sectors, two primary data. Prices would be, from prices we get returns, and then standard deviation of returns that we can transform into clusters. From prices, we can also compute what is called a z-score, and then the z-score can be sectorized or clusterized in three different ways, either from real sectors like industrial, economic, financial, or by sectors on standard deviation. Or we can also rank the z-score each date compared to the z-score in the entire universe. Those are three ways of doing this calculation of z-score. And what we want to be able to do is compute only one of those results by not executing the entire graph. So to code this previous toy model, this is what we did. Two classes called derivations. The first, basic, is simply reading the input files, so the primary data. And the second one, called temporary, is actually what we want to do with Dask. So we declare a variable object that take into as input an operator. Here, PCT delta will compute percentage variations on prices. And then we can combine those results into clusterizations. And the UML diagram of that looks like this. So you have two main classes. Derivation is the one I showed earlier, that will store a set of lazy memorizer objects like var or file var. And here, it's important to note where the task futures are created. That's up here in the build result method. The build result will be called by the call function. So if I have a lazy memorizer object and I call it, it will build the results. In the derivation, you can note that we have two inputs, so the list of variables. This means the full graph, the entire graph of computation. And another one, which is an optional argument, the subset. It's a list of names of variables we actually want to compute in the end. So that's our subset here. And it's taken into account what we call the derivation option this time. Now, where the magic happens is here. In build result, before submitting the future, the lazy memorizer will call its parents. So its parents are actually the variables it depends on. It means that the parent variable will be called, which itself will call its parents variable. So, for example, if I want here to calculate only the second clusterization, I call only this one, which itself will call z-score, which itself will call prices, which will read itself, then z-score will compute itself, then calc-def-by will compute itself, and we end up with this graph. Meaning we saved up a lot of computation time because we didn't load sectors and we didn't compute PCT delta, for instance. Now, Noureddine talked earlier about our real derivations. So our real derivations are, of course, a bit bigger than what I showed. This, for example, is a subset of a real derivation. And we can see the execution in the Dask dashboard here, for example. So here you can see that our schematics for the graph can highly be parallelized with Dask. That's a very good point. And if we run it on a remote cluster, we can also take benefit from auto-scaling that's kicking in now. And this is accelerated 10 times, so it fits into a presentation, but you can see that in less than 4 minutes, we managed to do an entire graph of computations. You might not have noted it, but at some point, the RAM stored up to 60 gigabytes of data. Now, if I go back to the presentation here, sorry. You can see on the graph the three operators I mentioned earlier. So for example, here you have a map, here a unary operator, and here an input operator. And as a conclusion, we can say that thanks to this wrapper, we're able to run subsets of the graph, which is actually necessary because the graph subset on a cloud cluster took 4 minutes. The full graph will take 20 minutes. In finance, gaining time is important if you want to trade before the concurrence. And just to mention, on the local computer, the graph subset would have taken 1 hour, and the full graph would have made our computer explode because it would have required 300 gigabytes of RAM at some point. Now, we also have a future announcement that we'll implement later on, the incremental run. We want to only process new data. That's not the case here now, I didn't show it, but in the future, that's what we'll be able to do. If we have new dates of data, for instance, and have, for example, a moving average, we don't want to compute it from the start from 10 years ago. We want to compute only the new data. This is a future enhancement. And that's all for us. Thank you.
Thank you.
Oops.
Thank you very much. If anyone has any questions, then please type them into the Q&A tab now. We have a few minutes left over, so we can wait for that. And after a few minutes, if there are no questions, then we will move on to the next talk. I have a comment myself. I work on Intake, and Intake has a new feature that hasn't been widely publicized yet called derived datasets that does some of the idea that you were presenting here of taking a dataset and doing something to it and presenting it as a new Dask object. In this case, in the Intake's case, it's about presenting it as a new data source in a catalog. Maybe there is some scope for collaboration or cross-pollination of the ideas there.
Yeah, that looks pretty great, huh?
Could you write in the comment section the name of the software you're talking about?
Yes, I will do. It's Intake.
Thank you.
There is a question here. It wasn't clear to me why you chose futures over delayed. Could you please say again?
I think I let Mike answer to that question.
Yeah, actually, that's that's a good question. Actually, so you understood that we use a thin wrapper to start our future, and we could have would have been delayed would have been possible actually to call the persist method for each delayed. So I think I'm not sure now with the experience of Dask. I will use future again, but it works actually. So I think both are good. So yeah, as I said, we can handle the how long the life of the future according to object pointing to future. So maybe it's easier to handle the life of object than calling persist or clean. You know what I mean? It's implicit. Yeah, I think that is a reason to use implicit the persistence implicitly with the life of the object. Yeah.
The next question, is the wrapper something that you plan to open source?
Oh, I think we'll be glad to do that. So, yeah. So open source makes sense if other people participate to this to the platform, I guess. So, or we can just share the information. So that would be, yeah. If you can send the details about that, so we can keep in touch.
Yeah, I do encourage people to continue the conversation on Slack and gather in other forums that we have here. But thank you very much for the talk.
Thank you for receiving us.
Thank you.